So today we're going to look at the second subtopic for heat, which will be specific heat capacity. Now, specific heat capacity is defined as heat required to change temperature of 1 kilogram of substance by 1 degree Celsius. Okay, so heat needed to change temperature of 1 kilogram substance by 1 degree Celsius. Okay, now the SI unit for specific heat capacity is joule per kilogram per degree Celsius. Joule per kilogram per degree Celsius. Now, what is the meaning of this specific heat capacity? So we look at an example. Now, so let's say if you have two material with different specific heat capacity. So let's say you have material material A and material B. Now, so the specific heat capacity. Okay, so let's say for A will be 100 joule per kilogram per degree Celsius. Okay, so let's say for B will be 500 joule per kilogram per degree Celsius. Okay, now, so what is the meaning of this value? Now, so now if we look at A, right? If we look at A, now what is the meaning of 100 joule per kilogram per degree Celsius? That means, right, for A, right, if you want to increase, right, okay, increase, okay, 1 kilogram of mass, right, okay, by 1 degree Celsius, you need 100 joule. Okay, okay, that means for A, right, if you want to increase, sorry, put it this way, let's say for 1 kilogram Fa, okay, that means 1 kilogram Fa, if you want to increase the temperature, okay, temperature by 1 degree Celsius, you will need 100 joule of heat. Whereas for 1 kilogram of B, okay, so if you want to increase, okay, temperature by 1 degree Celsius, you need 500 joule heat. Okay, that means for every kilogram of B, if you want to change the temperature by 1 degree Celsius, you need 500 joule of heat. Whereas for A, right, for every kilogram of A, that means if you want to change the temperature, whether increase or decrease, you need 100 joule of heat. Okay, so when you want to increase by 1 degree Celsius, you need to give 100 joule of heat. When you want to reduce temperature, it must release 100 joule of heat. Okay, that means, okay, so here, right, if you see A, right, for to increase 1 degree Celsius, you need 100 joule of heat. That means if you give A 500 joule of heat, the temperature increment would be 5 degrees Celsius already. Okay, whereas for B, right, if you give 500 joule, the temperature increment is only 1. But right, for A, if you give 500 joule of heat, it will have increased by 5 degrees Celsius. That means the changes in temperature is greater. Okay, so what happened is we can say that, okay, okay, so we can say basically like this. So material, right? Material with low specific heat capacity. Okay, material with low specific heat capacity, easy to become hot or cold. Okay, so easy to become hot or cold. Okay, that means it become hot or cold easily. Okay, so that's what is meant by low specific heat capacity. Okay, whereas, okay, material with high specific heat capacity, okay, difficult to become hot or cold. Okay, so material with high specific capacity, okay, difficult to become hot or cold. Okay, the material with low, that means easy to become hot or cold. Okay, so that means the smaller the specific capacity, easier to become hot, easier to become hot, cold. Okay, so okay, now so basically specific heat capacity, the short form is C. So the short form of specific capacity is C. So if you look at the unit, right? Okay, if you look at the unit, so if you look at the unit of C, right? Okay, so the unit for specific capacity is joule per kilogram per degree Celsius. Okay, the unit. Okay, so this one, if I write in the form of fraction, it becomes joule per kilogram per degree Celsius lah. Now, joule basically is the unit for heat. Okay, represented by Q. Kilogram is the unit for mass. Okay, represented by M lah. And then degree Celsius will be the unit for temperature. Okay, change in temperature. Okay, which will be theta lah. So if the whole thing I write in the form of what they call it, quantities, right? So it becomes C equals to Q over M theta. So if you cross multiply what you get Q equals to MC theta. Okay, so Q equals MC is the formula, okay, used to calculate the heat needed to change temperature of substance, to change whether increase or decrease. So Q equals to MC theta, mass with M per kilogram, C will be specific heat capacity, theta will be your change in temperature in degrees Celsius. Okay, so we look at how to calculate, how to use this formula. Now, example 1. Now, calculate the amount of heat that must be transferred to 2 kilogram metal to raise the temperature from 30 to 70. So this one very simple. Q equals to MC theta. So the mass will be 2. The C will be 500. And then the theta will be 70 minus 30. Okay. So you press calculator, you get the answer lah. Okay, so it's at 4,000 joule. Next, 8.4 times 10 per joule of heat energy raises temperature of 4 kilogram of water from 40 to 90. So what is the specific heat capacity? So use the formula Q equals to MC theta. So Q will be 8.4 times 10 to the power of 5. Okay, so the mass will be 4. Specific capacity don't know. So your theta will be 90 minus 40. Okay. 8.4 times 10 to the power of 5. Okay. Divide with 4 times 50. Okay, so it's 4,200. Joule per kilogram per degree Celsius. Next, 0.2 kilogram of water at 100 is mixed at 0.25 kilogram of water at 10. So what is the final temperature? Now this one involves situation where you have hot, okay, object mixed with cold object. Okay, so hot object mixed with cold object. So basically how to do this kind of question, right? Now, the first thing is we need to assume when you have hot object, okay, mixed with cold object, what happens is we're going to assume that all the heat from the hot object is transferred to the cold object. That means all the heat from hot will be transferred to cold. That means there's no heat loss to surrounding. Okay, that means all the heat from the hot water will be transferred to the cold water. So you're going to say, you're going to assume, because it's like this. Okay, so we're going to assume heat okay, so heat loss by hot water equals to heat gain by cold water. Okay, so you're going to use mc theta equals to mc theta. Okay, yeah. Now, what is the mass of the hot water? 0.2. Okay, now if you look at the question, they never give you specific heat capacity. Why? Because actually for this question only because both involve the same material, water and water. So the C and C can be cancelled off. Okay, now how about the changes in temperature? Now if you look at the graph of temperature against time, okay, so the hot water was 100 degrees Celsius, whereas the cold water is 10 degrees Celsius. So what's going to happen is the hot water, the temperature will reduce, the cold water, the temperature will increase until they reach thermal equilibrium, that means same temperature. Let's say the final temperature is X, this is what we're going to find. Okay, so these are the changes for hot water. Okay, the temperature. Okay, so this one will be the cold water. Okay, so it become mc theta equals to mc theta. So the MC and C can cancel. Okay, why? Because they are same. So what will be the changes for hot water? The changes will be 100 minus theta. Okay, now what will be the changes in temperature for cold water? So changes is difference. So it's minus. So x minus 10, not 10 minus 10, because x is greater than 10. Okay, now this one, why 100 minus x? Because 100 is greater than x. For this one, x will be greater than 10. So it will be cold water, the mass is 0.25. Okay, x minus 10. So what do? You open the bracket. So 0.2 times 10, you get 20. X is right. Okay, this one's supposed to be x. Okay, so minus 0.2 x equals to 0.25x minus 2.5. Okay, so you open the bracket. So all the x you bring one side. So I'm going to bring this x here. And then the 2.5, I'm going to shift to this side. Okay, so it's going to become 20 plus 2.5 equals to 0.2x plus 0.25x. So 22.5 equals to 0.45x. So x will be 22.5 divided with 0.45. Okay. So 22.5 divided 0.45. Okay. So you get 50 degrees Celsius. Okay, 50 degrees Celsius. Okay. So this is how you do lah. Okay, involving changes in temperature. What do you call it? To find temperature, final temperature when you have hot object mixed with cold object. So the basic idea is very simple. You take the heat lost by the hot object equals to heat gained by cold object. Okay, so in this case, it can be the same material, water, and water can be different material. But if different material, that means you have different specific capacity lah. Okay, but this time because both are water, so you can, okay, what do you call it? You can cancel off if the same material for specific capacity. Okay, next we look at how experiment, right, to determine the specific heat capacity of an aluminium block. So what you given, you given a heater, okay, and then okay, so you put thermometer inside one hole, the other one you put heater lah. So what you need to do is you need to calculate the mass first, okay, and then what you do is you what do you call it, determine the initial temperature, and then let's say you, okay, after that you on the heater for a certain period of time, and then you record the time as let's say 1 minute, 2 minutes, or 5 minutes, or whatever, okay, whatever value you want lah. And then after you stop, okay, you wait until you get a maximum final temperature. So final temperature will be theta 2. Theta 1 is initial temperature lah. Okay, yeah. So basically what you're going to do is you're going to use the formula Q equals to MC theta. Okay, now so this Q will be the heat, okay, heat supplied by heater. Okay, so heat supplied by heater. Okay, now how to determine the heat supplied by the heater? Now, from the formula, we know that power is defined as energy over time. Okay, so power is energy over time. So if you want to find the energy, it will be the power times time. Okay, so the heat energy, okay, supplied by the heater is given as power times time lah. So basically it's electrical energy, electrical energy converted to heat. So basically you have the power, you have the time, you can find the heat supply. So it becomes PT equals to MC. So your theta will be your final temperature, theta 2 minus theta 1. Okay, so that's why you see, okay, what you do, you bring this theta 2, theta 1 and M down lah, because that's why you get this formula. Okay, so specific capacity is PT over M times theta 2 minus theta 1 lah. Okay, yeah. Now, so when you use this formula, right, there are few assumptions you have to, okay, there's assumption that you need to apply here. So we assume that there's no heat loss to surrounding. That means all the heat from the heater is supplied, all the heat from the heater is absorbed by the aluminium. That means all the heat here is absorbed by the aluminium block. So no heat loss to surrounding. So that is our assumption. Okay, the first one. Okay, next. After that, okay, for precaution, right? Okay, this one also important, right? So what happened is, okay, in reality, heat will be lost to surrounding lah. So what we must do is we must insulate the aluminium cylinder. So we insulate with cloth lah. We insulate with cloth. Okay, basically we want to reduce the heat loss. We cannot overcome, we can reduce lah. And then one more thing, right? If you look at the hole where we put the, what do you call it, thermometer and the heater, you need to put some oil. Okay, yeah. So why we need to put some oil is because, see, assuming this is your aluminium block. Okay, so this is where you put your heater. Okay, so you put your heater here. Okay, so you put your heater, right? Now you see, right? If you don't put anything, this region will be air. So we know that air is a poor conductor of heat. So what happens when you on the heater, right? So it'll take a longer time for the heat to be transferred to the aluminium block. Okay, so it takes a longer time for heat to be transferred to aluminium block. Okay, why? Because air is a poor conductor. So that's why we put oil. So inside there you put oil lah. Okay, because for better thermal contact. Okay, for better thermal contact. Same here lah. Okay, thermometer is recorded, is used to record the temperature. So this is your thermometer. So if you don't put anything, here is air. So it takes a longer time for the heat from the aluminium to be transferred to thermometer. Okay, because air is a poor conductor. So that's why you put oil. Okay, so you put oil inside there. So for better thermal contact, that means the heat can be transferred faster to the thermometer, so you can get the reading faster. Okay, so for better thermal contact. Okay, so that's the first one. The second one, sorry. Okay, yeah. So you need to put oil inside the hole because for better thermal contact. Okay, one more thing, right? When you do the experiment, the value of C calculated here, okay, that means that you calculate, is usually higher than the actual value. Actual value. So why? Because you see, when we use this formula, we assume that all the heat from the heater is absorbed by the aluminium. But in reality, this is not going to happen. Okay, it's not going to happen. So if we use Q equals to MC theta, okay, so we know that Q over MC equals to theta. So in reality, right? Okay, so what's going to happen is, in reality, heat will be lost to surrounding. So what happens if heat lost to surrounding? That means, assuming okay, now assuming the heater is supplying 1000 joule of heat. Okay, 1000 joule of heat. So out of this 1000 joule, 1000 joule won't go to the aluminum. Maybe the aluminum get 800. So some of them is lost to surrounding. So let's say 200 joule is lost to surrounding. So what happens is the aluminum is getting lesser amount of heat. Okay, so aluminum is getting lesser amount of heat. So it's not getting the actual amount of heat. So what happens is, that means the value of Q is, sorry, okay. So what happens is, sorry. Okay, so what happens is the changes in temperature will be lesser. Okay, changes in temperature lesser, because if you give 800 joule, the temperature increment is not going to be greater, it's going to be lesser. So that means the theta will be lesser. So change in temperature will be lesser. So because of that, the value of C will be higher. Okay, because it doesn't give the actual amount of heat. So only, okay, some amount of heat will be given, the other one will be lost to surrounding. So that means your theta will be lesser, so your C will be higher. So that's why we need to insulate. Okay, that means we need to wrap with cloth to reduce heat loss to surrounding. Okay. Okay, so we look at an example on how to use this formula. Now, a 2 kilowatt 140 volt electric heater used to raise temperature of 3 kilogram of water if power supplied for 8 minutes. What is the increase in temperature? So this one you can use Q equals to MC theta. So Q becomes PT. Okay, so the power will be 2000. Okay, the time will be 8 times 60. Okay, and then the mass will be 3. The value of C is 4200. Okay, and then you can find the theta. Okay, so 2000 times 8 times 60 divide with 3 times 4200. So 76. Degree Celsius. Okay. Okay, 72.6 degrees Celsius. Okay. Now another example. Now a 1.2 kilowatt immersion heater is used to raise temperature of 2 kilogram of water in a copper container. Okay, of mass 0.05 by 20 degrees Celsius. So calculate the time taken to increase the temperature of water. Now this one, right, they are using copper. Okay, so copper is a good conductor of heat. Now, if the container is polystyrene or whatever, okay, polystyrene or polystyrene or plastic, we can ignore the heat absorbed by the cup. But in this case, we cannot ignore the heat absorbed by the cup. That means what we need to do is we're gonna, okay, so that means we're gonna say heat, okay, supplied by heater, right, equals to heat absorbed by water, and then plus heat absorbed by container. That means we have to consider the heat absorbed by the container and also by the water. So heat by heater is PT. PT. So equals to MC theta. This is by water, right? Plus MC theta of container. That means you have to assume both. Okay, heat absorbed by water and also by the container lah. So basically, right, your power is 1002, and then times T, right? Okay, mass of water is 0.2, and then times 4,200 times changes temperature 20, plus, okay, heat absorbed by this one 0.05 times 400, and then times 20. Okay, so 400, is 400 times 20. So what you do is, okay, so just, so 0.2 times 4,200 times 20, plus 0.05 times 400 times 20. So divide with 1,200. So you get 14.33. Okay, 14.3 seconds. Okay, 14.3 seconds. So for this one, right, you have to consider the heat absorbed by the container and also by the water. Okay, now, so we look at the application of specific heat capacity. So basically, right, if you look at Q equals to MC theta, okay, MC theta. So Q over MC equals to theta, right? Now, object with higher specific heat capacity, so the change in temperature is less. That means difficult to become hot, difficult to cool down. Q over MC equals to theta. Object with lower specific heat capacity, changes in temperature will be great. That means easy to become hot, easy to okay, cool down. Okay, easy to become hot, easy to cool down. Okay. So basically, right, if you look at cooking, okay, instrument like this, right? So the handle must have high specific heat capacity. Okay, so why? Because it doesn't become hot easily. So the theta will be lesser. Whereas the pot, we want it to become hot easily, so must have smaller specific capacity. So that the theta or the change in temperature is great. Okay. Okay, next we look at radiator. Now radiator basically is to cool down the engine of the vehicle. So what happens is, okay, you have a radiator tank. So what happens? The water, right? So water is pumped, okay, to this area which is very close to the engine block. So what happens? The heat from the engine block will be transferred to the water, okay, and then what happens? The water will be pumped back towards the what do you call it? Radiator tank lah. So now the water become hot. Okay, here the water is cold, here the water is hot. So in order to cool down the hot water, you have a radiator fan. So the radiator fan, what happens? It cools, okay, it suck in the air, okay. So it will suck in the air so that the heat from the hot water will be transferred to the air, okay. So the heat from the hot water transferred to the air. So what happens? The water will be cooled down, so the water can be pumped back, okay. Okay, next, the formation of sea breeze and land breeze, right? Now, sea breeze happen during daytime. Okay, so during daytime, right, what happened? Land is warmer. Okay, so land is solid. So the land is warmer. So when the land is warmer, okay, why? Because the land has smaller specific heat capacity. So the land is warmer compared to the water. So water will have higher specific capacity compared to land. So what happened? Because of that, the air above the land will be hot. Hot meaning it will have low density lah. Okay, low density. Okay, so what happened? Because low density, what happened? The air will rise up. Okay, so when the air rises up, what happened? This area, right, becomes something like a semi-vacuum. Okay, because air goes up, it becomes something like empty lah. So it becomes semi-vacuum. So because of that, this region will be low pressure. Okay, low pressure. So what happened? Because this is low pressure, so the wind will blow from sea to land. Okay, so wind will blow from sea to land. Okay, now during night time, what's going to happen is the other way around. So water is hotter compared to land because at night time, daytime, land and water will absorb heat from the sun. But night time, they will release heat. Okay, they will release heat. So when they release heat, what happens? Same thing lah. Lower specific capacity, that means easier for you to cool down. So the land is cooler, okay, compared to water. So water is hotter compared to land. So what happened? Air above here will be lower density. Okay, lower density, because air here will be hotter. So hotter, low density. So low density, what happened? The air rise up. So this one creates an area of semi-vacuum, okay, or low pressure lah. So here become low pressure. Okay, so the wind will blow from land to sea. Okay. Okay, now we look at example of structured question involving this. Now, two blocks P and Q, figure 1, have the same mass. They are immersed in boiling water for a long time. So P and Q are then transferred into beaker X and beaker Y respectively, as shown in figure 2. So the mass of water in both beaker X and Y is 0.25 kilogram, and the initial temperature of water in each beaker is the same. Okay. So the capacity of P is 900, Q is 390, the capacity of water is 4,200. So state the initial temperature of the blocks. So what happens is the blocks are put inside boiling water. Okay, so we know that boiling water, the temperature will be 100 degrees Celsius. So that means the two blocks will have the temperature as the boiling water. Okay, so they will have the same temperature as the boiling water. So that means the answer will be 100 degrees Celsius. Next, why is the final temperature of the water in beaker X higher than beaker Y? Okay, now, so why temperature of water in beaker X higher than beaker Y lah? Okay, this is beaker X, this is Y. Okay, now, so we know, right? Okay, why the temperature in X greater than Y? So definitely, right, P will release more heat. Okay, P releases more heat in water compared to Q. So Q will release less heat. So that's why here the water is hotter compared to this. Now the question is why P releases more heat compared to Q? Meaning, when P inside the boiling water, right, we transfer here, right? So that means inside the boiling water, what happened? P absorb more heat lah. Okay, P absorb more heat. Then only P, when you transfer here, can release more heat. That means inside the boiling water, Q is absorbing less amount of heat. So that's why when it goes here, it releases less amount of heat. Okay, so P inside the boiling water absorb more heat compared to Q. So the reason is because of this. Q equals to MC theta. So right, if you look here, P has higher specific heat capacity. So that means when you have higher specific heat capacity, that means inside the boiling water, P absorb more heat. Okay, P absorb more heat. Okay, when it's inside the boiling water because of higher specific capacity. Whereas Q absorb less amount of heat because lower specific capacity, so absorb less amount of heat. Okay, so meaning why temperature, okay, of X greater than Y. So there are many answers you can give. You can say, okay, first P, P has higher specific heat capacity. Okay. Then Q. Okay, you can even say P releases more heat than Q. Okay, when transferred into beakers of water. Okay, we can see P absorb more heat than Q when they are in the beaker with boiling water. Okay. Okay, so these are the option answer. So P absorb, okay, more heat than Q when they are in the beaker with boiling water. Okay. Okay. Next. Calculate the rise in temperature of water in beaker Y in the block. Okay, if block Q releases 8,400 joule of heat energy. So this one you can use Q equals to MC theta. So 8,400. So the mass is 0.25 times 4,200 times theta. Okay. So 8,400 divided by 0.25 times 4,200. So 8 degrees Celsius. Okay. So state one assumption. So this one we assume no heat loss to surrounding. Okay. Now we look at example 2. Now diagram 4 shows a baby bottle that is filled with 0.05 kilogram of hot water. The hot water in the bottle is then mixed with 0.03 kilogram of cold water to prepare milk for the baby. So the temperatures of hot water and cold water are shown in the water dispenser. So what is meant by specific heat capacity? So this one you can refer to this. Okay, heat required to change temperature 1 kilogram of substance by 1 degree Celsius. Okay, so you can refer to this. Next. Okay, calculate the final temperature of the water. So we have a situation hot water mixed with cold water. So we're going to start off with heat loss by hot water equals to heat gain by cold water. Okay. So it's going to become MC theta equals to MC theta. So since got water and water, so you can cancel the C. So the mass of the hot water, hot water is 0.05. 0.05 times. Okay, so the temperature of the hot water is 90. Yeah, you can see here temperature is 90. So we put 90 minus x equals to cold water is 0.3 times x minus 30. So cold water temperature here, hot water temperature here. So okay. So if you want to make things easier, you just keep the 90 minus x. The 0.05 times, right, you bring down here. So it becomes 0.3 divided with 0.05 times x minus 30. Okay. So 0.3 divided with 0.05. So we get 6. Okay. So that means 90 minus x equals to 6 x minus 30. Okay. So 90 minus x equals to 6x minus 180. Okay. So bring the x here, bring the 180 here. Okay. So 90 plus 180, yeah, 270. To 7x. Okay. So 270 divided by 7. So you get 38.6. Okay. $38.6. Degrees Celsius. Okay. Next, the milk is given to a baby who drinks only half of it. Okay. So what happened to the temperature of the leftover milk in the bottle after a few hours? After a few hours. So give one reason for your answer. So you can say the temperature after a few hours. So what will happen to the temperature? So you can say same as the temperature. Okay, I can even say decrease lah. You can say heat loss to surrounding. Okay, we can say milk achieve thermal equilibrium. Okay, with surrounding. Okay, we just can say simply lah. So heat is lost to surrounding. Okay, so what happened to temperature? That means same absolute temperature. You can say decrease lah. So why? Because heat lost to surrounding or milk achieve thermal equilibrium with the surrounding lah. Okay, so suggest one way to keep the milk warm for a long time. So give a reason. So you can say wrap. Okay, so wrap the bottle. Okay, with cloth. Okay, you can say cloth, or you can say insulator also can. Okay, so reason reduce heat loss surrounding. Okay, we can say wrap the bottle with cloth, okay, or put inside polystyrene material, polystyrene also can. Okay, all this to reduce heat loss to surrounding. Okay, we look at number 27. Now, diagram 7.1 shows a cooling pad used to lower temperature of person having fever. The pad consists of a gel and is cooled in a refrigerator before it is placed on the forehead of the person to remove it. So what is meant by heat? So heat is a form of energy. Okay. Explain how heat is removed from the forehead of the person. So you can say temperature of person greater than cooling pad. Okay. And you can say there is transfer heat person. Okay, so temperature of person greater than cooling pad. So because of that, there's net transfer of heat from the person to the cooling pad. Okay, next. So the mass of the gel in the pad is 0.3, capacity 4,300. So initial temperature is 15. Okay, calculate the amount of heat. So this one just use Q equals to MC theta. Okay, so so the mass will be 0.03 times 4,300 and then times 56 minus 15. So 0.03 times 4,300 times 36 minus 15. So 2709. Now, it is suggested that the cooling pad should be modified so that it can remove heat from the person, can remove more heat. So, give two suggestions. So, for this one, right, Q equals to MC theta. Okay, so first you can say okay, use cooling pad with bigger area. Okay, so wider reason, wider area of contact. Okay, or bigger area of contact lah. Okay, that means use a bigger cooling pad. Okay, use a bigger cooling pad so that bigger area of contact. Okay, with the person. Okay, bigger contact with the person. Okay, or bigger area of contact with the weight of the person lah. Yeah. Now next, right, if you want to remove heat, you must use okay, gel with higher specific heat capacity so that can absorb more heat. Because the highest the C, the higher the Q. Okay, so use gel with higher specific heat capacity. Okay, so reason can absorb more heat. Okay, so can absorb more heat. Okay. Okay. So next, a student is investigating the specific heat capacity of three metal blocks X, Y, Z. Each block has a mass of 1 kilogram. A heater and a thermometer is inserted into the block as unit figure 4.1. So the heater has a power rating of 15 watt. Initial temperature of the block is measured. The heater is switched on for 10 minutes and the final temperature of the block is recorded. This procedure is repeated for the other two blocks. So the student results are shown in table 4.1. Okay. So fill in the blank to complete the sentence. So specific capacity is the heat needed to change temperature of 1 kilogram substance by 1 degree Celsius. Now, by referring to the result, identify the block with the greatest specific capacity, give your reason. So if you use the formula Q equals to MC theta, so Q equals to MC, Q over MC equals to theta. So that means higher specific capacity, smaller change in temperature. Higher specific capacity, smaller change in temperature. Okay, so smaller change in temperature is X lah. Okay, X. Okay, so the answer will be X lah. So reason because smallest change in temperature. Okay. Now calculate specific capacity of the block identified. That means for the block X lah. Okay. So this one you can use Q equals to MC theta. So you see, right, there is power. So power 15 watt, the time is 10 minutes. Okay, so 25, 15. So you change Q to PT. So PT equals to MC theta. So the power is 15, the time is 10 minutes. So 15, so the time convert to second, so 10 times 60. So the mass is 1, the C don't know. And then so your theta will be 25 minus 15. Okay, so the C will be, okay, 15 times 10 times 60 divided with 25 minus 15. So your answer will be 900. Okay, joule per kilogram per degree Celsius. Okay. Now, due to the energy losses, the specific capacity accepted in this investigation are different. So the student decide to improve in order to obtain a value closer to the accepted one. So suggest a possible improvement and then state the effect in this state the effect of this improvement on the final temperature. Now, if you look here, right, what happened is that the metal block is not covered with any insulator. Okay, metal block is not covered with any insulator. So metal block is not covered. That means there's heat loss to surrounding. Okay, a lot of heat loss to surrounding in this case. So we need to cover the metal block with insulator. Okay, now so you can say okay, wrap wrap metal block with cloth. You see, okay. So so this one is to reduce the heat loss to surrounding and then they ask you state the effect that this improvement have on the final temperature. So that means when you wrap with cloth, right, that means heat loss to surrounding will be less. That means your final temperature will be more, okay, or higher. Okay, higher. Okay, so final temperature will be higher. Now we look at 23. Now diagram 8.1 shows a 500 watt electric heater being used to heat a beaker of water on a compression balance. So state the energy involved. So the energy involved when using the heater energy change, right? So say electric energy to heat energy. Next. Now the mass of water is 0.5 and the specific heat capacity of water is 4,200. Initial temperature of water 30. Calculate the energy absorbed by the water to reach the boiling point. So this one you can use Q equals to mc theta. So the mass is 0.5. This is 4,200. And then your change in temperature is 100 minus 30. Okay. So you'll get this one. So 0.5 times 4,200 times 70. Okay. So 147 joule. Okay. Next. Okay, when the water reach point, okay, this question we ignore for a while because we haven't done latent heat yet. Okay, we haven't learned latent heat, so I'll skip this for time being. Okay, so we haven't learned latent heat, so we skip that for a while. B. Okay, we look at D. Q, R, S are three different hot plates. So these hot plates are used to heat with each other. So table H shows the characteristic. So initial temperature of the plate is 30, and then the plates are ready to be used when the temperature reaches 200. So calculate the time taken to reach 200 degrees Celsius for each plate. So this one, basically what you do is you're going to use Q equals to mc theta. This one you change to PT so PT equals to mc theta. So what would be T? T equals to mc theta divided by P. Okay, so that means all this is mc theta divided by P. That means if you want to find the time for Q, so the mass here will be 3, the C will be 390, and then your changes in temperature will be 200 minus 30. Okay, divide with the power. So the power is 600. Okay, so the 3 times 390 times 170 divided with 600. So you get 331.5. Okay, so for R same, so T will be, so the mass is 2.5, the specific capacity is 900. Okay, change in temperature same, 200 minus 30. And then this one will be 1,200. So 2.5 times 900, 170, 318.75. Okay, so for S also same. So the T will be 4 times 400. So 200 minus 30 divided with so the power is 900. So 4 times 400 times 170 divided with 900. So you get 302. Okay, so you can see that S have the shortest time. Okay, to reach 200 degrees Celsius. So S has the shortest time to reach 200 degrees Celsius compared to the other two. So based on your answer, right? So they ask you to choose so S lah. Okay. So reason shortest time. Time to reach 100 degrees Celsius. Okay, 100 degrees Celsius. Okay, now we look at number 24. Now, table 8 shows the type of pot and their characteristic. So, what is the meaning of specific heat capacity? So, this one you can refer to the earlier one. Okay, next. Based on table 8, state the suitable characteristic of the pot if it is to be used to cook something rapidly. So, give reason for the suitability of the characteristics. Okay, so the material of the pot, there is clay and also there is copper. So, you see, clay got higher specific heat capacity. Copper is lower. That means copper get heated up faster. Okay, so we will choose copper. Okay, copper. So reason, lower specific heat capacity. Okay, so material to make the handle. So material, there is clay and polymer, right? So polymer lah. So we choose polymer. Okay, polymer. So reason does not become hot easily. Okay, I can say better insulator of heat. Good insulator of heat or better insulator of heat. Okay, mass of the pot, right? So we can use smaller mass. Okay, if not, if too high, that means difficult to carry. Okay, small. So reason, easier to carry. Okay, or lighter also can. Okay, not heavy also can. Okay, next. So the pots are heated using a electric hot plate of power 800 based on information. Calculate the time taken to achieve a temperature rise of 90 degrees Celsius. So this one you can use Q equals to MC theta, right? So you change Q to PT lah. So PT equals to MC theta. That means your T will be MC theta over P. Okay, MC theta over P. So for clay pot. So mass is 2.5, 3.5, 900. So this one will be 3.5, 900. Change in temperature is 90. Yeah. Then the power 800. Okay, 800. Okay, 800. Okay, for the copper, 2.5 times 390 times 90 over 800. So find the answer. So 3.5 times 900 times 90 divide with 800. Equals to 354.3 seconds. 2.5 times 390 times 90 100 109.7 seconds. So determine the suitable pot. Okay, so the answer will be copper lah, or shortest period of time. Okay, shortest period of time. Okay, now number 25. Now diagram 8 shows two models of frying pan. So what is the meaning of specific capacity? So this one you can refer to this one definition just now. Now based on the information, state the suitable category of frying pan that is used to cook food faster. So the type of surface and reason. So it's dark and black, bright. Sorry, dark and bright. So we choose dark surface. Okay. So dark because good absorber of heat. Okay. Now specific heat capacity. So specific capacity must be low. Okay. So reason become hot faster. Okay. Based on answer, determine the model, give reason. So the model will be B. Okay. So reason become hot faster. Okay, or easily to become hot. Okay, become hot faster or easily to become hot. Now, a kettle contains 0.5 kilogram of water. So the average heat absorbed by water is 16 joule per second in 25 minutes. So calculate the amount of heat absorbed by water. So the amount of heat absorbed. Okay, this actually, right, if you look at it, right, this is 16 joule per second. Power is defined as energy over time. Okay, so the unit for energy is joule, the unit for time is second. So this one, when you bring up, right, what happens, you get joule per second. Okay, so joule per second is the unit for power, so which is also known as watt lah. Okay, so unit for power is joule per second or watt. Okay, so this one is power. So you want to find energy lah. So energy is power times time. So it'll be 16 times 25 times 60. Okay, so 16 times 25 times 60. So you will get 24,000 joule. Okay, now the increase in temperature of water. Okay, so this one you can use Q equals to MC theta. So your Q will be 24,000. So the mass is 0.05. The C is 4,200. So you can find your theta. Okay. Okay, sorry. The mass is wrong. The mass here is 0.5. Okay, 0.5, sorry. Okay, 0.5. 24,000 divided by 8, 0.5 times 4,200. So you get 11.4. Okay. So this will be answer. Okay. So this is example of structured question for specific heat capacity. Okay. So So the next video we will look at the essay question for specific heat capacity. Okay, so that's all for now.